Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with your Unit 2-1 homework here. We're going to chat about numbers 10, 11, and 12. So number 10 says something about a boat moving through the water. So start with a picture. I'm going to draw just a quick picture, top view here of my boat. Okay, and it's got a motor on it, all right, and a propeller back here, and all right. And it says that there's a 1725 Newton force push by the water on the propeller. So what that means, there's a force in this direction. I'm going to put F sub P, force on the prop. This is a number given in your homework. Now, it says there's a resistive force due to water around the bow. So basically, you know, the boat's pushing a wake up. And so that wake, or that force interaction, would be to the right on the water, but it would be to the left on the boat. So I'm going to call this F sub W, force on the water. And again, forces have what are called lines of action. You can draw this thing anywhere you want along this line. Now, Newton's second law, sum of all, we can apply that. Sum of all forces equals ma. There's no reason to do anything other than write positive. And then you just use your free body. This is my symbol for looking. You look at your free body. You got this one to the right, given in the problem, minus this one to the left. A mass given, so you should be able to find the acceleration of that boat, no problem. Part B and C, these are questions about motion. B says, how far will it go? C is, what will its velocity be? So now we're going to do what I call the motion study. Draw a velocity graph. If you're in my class, how many times have you heard me say that? Right? Velocity against time. Ask yourself at t equals 0. Part B, it says starting from rest, so at t equals 0. The velocity is 0. I'm not going to do the rest of this for you. You have to decide, you have to figure out how to get those graphs done on your own. And then once you have the acceleration from over here, ask yourself, how does that relate to that graph? Right? That's going to, and then use, that's going to allow you to solve something. And then the, where it says, how far will it go? Okay, that's going to be a change in x. That's a displacement. Ask yourself, what property of that graph? How have we been doing that? So that should get you through number 10. Okay, 11. Whoops. Well, it's all right. So I'm going to draw a quick picture here for number 11. There is some sort of object. All right, it has, somebody is applying some sort of external force to it. So somebody's pushing, pulling, doing something. They're applying a force in this direction. This force is given in the problem. That's some number given. There's an angle theta here, also given in the problem. Okay, now you have to draw the rest of the free body, all right? The gravitational force, straight down. All gravitational forces are straight down. Well, drawn within, like at the surface of the Earth. Maybe something like this. I usually draw them mg, or you can call it the weight, or you can call it the force of gravity. Any of those are perfectly fine. Okay. Here's a surface in contact. That's going to give you what's called a normal force. That normal on the block goes maybe something like this. Whoops. Now, where you draw it is kind of up to you. Again, they have what's called line of action. You can put that normal anywhere along that line. Now, it's pretty easy to show. Let me go through a quick numerical example. Let's say that theta were 20 degrees. This triangle right here, that would make this one 70 degrees. But from here to here is 90. That would make this one 20 degrees. The moral of that little story is whatever this angle is right here, this one's going to be the same. Now, In this problem, this object is pulled up the plane. Does it say anything about accelerating? I'm going to try to read this. There's no friction, and what is the acceleration? Okay, so the free body's basically done. So what you want to do now is write a force equation. Sum of all forces equals mass times acceleration. And my standard rule of thumb for this is identify the acceleration direction, call that positive. This thing is probably accelerating like this. Now, not having ran the numbers, it's actually conceivable that it's accelerating this way. I haven't ran the values yet. I'm going to assume accelerating up to the right. When you write this force equation, this one is already fine. It's parallel to the x-axis, just like we're working on, no problem. This one makes a right angle to the x direction, so it will not show up in this equation. This one, a component does. So you have to draw that thing with components that are parallel to this and this. I'm going to let you folks do that as it's your homework problem. That should give you a pretty good chance at getting that one done. Let's see. Let's chat about number 12. So it goes through a bunch of cases. One, block on a level surface. So let me see here. Put my level surface here. Put a block on the surface. I like these to have a little depth to them. All right, and what you're going to do, let's see, it says calculate the magnitude of the force on that block. And it's, the mass of that block is given. So what you do is draw a free body of the block here. Oops. It will have two forces on it, one up, one down. And then it's not going anywhere, so the net force on it's 0. That'll get you the normal force. Okay, part B. Let me do this. Part B, it's sitting on an angled surface, and it says, mine says 25 degrees, 26 degrees, something like this. Yours will be some different value. Now, you're going to have to kind of redraw the free body. And this thing's resting now. So the only way this thing could be resting is if there's a frictional force. So I'm gonna give you some hints here. So the frictional force that goes in this picture, this is the line of action for it. It acts along here. And hopefully it's obvious what direction it is. The gravitational force, the line of action looks like this. Draw that one in there as usual. And the normal force, remember the normals always make a right angle. So the line of action for the normal looks like this. Draw those force vectors, and it says to find the normal force. So what you want to do is sum up forces in the direction of the normal this way. Call that positive. And because it's not accelerating, that vector sum is 0. Part C. Resting on the floor, but in an elevator that's accelerating, okay? So I'm going to use this picture. Make this C. So in part C, right, this is part of an elevator like this, and the whole system is accelerating, I believe, presumably up. And that's a given value. Draw your free body of this object. And again, you just ignore the elevator. It's about this object right here, right? It's got a gravitational force. Remember, the line of action for the gravitational force is right along this line. Should go right through this thing's geometric center. Again, surface and contact. So you're going to have a normal. Decide which way to put that normal on this object. Hopefully it's obvious. Then you write your force equation. Sum of all forces equals mass times acceleration. And remember Captain Rod's rule of thumb, right? I call them carrots. Captain Rod's rules of thumb. One of them is identify the acceleration direction, call that positive. So when you write your force equation, there's going to be two things over here, a normal and the mg, and then equals ma. That should definitely get that problem done for you. So I'm going to go ahead and stop that video right there. Hopefully that will help you get these problems done. Have a great day.